Good day, everyone. My name is Cheryl Dorsey Champon, and I'm here with my group members. Each person will introduce themselves. Today, we're going to talk about virtual memory and paging. And in our presentation, we're going to cover the concept of virtual memory, page faults and replacement, page replacement policies, multi-level paging, segmentation and segmented memory, and finally, virtual and segmented memory. I'll begin by talking about the concept of virtual memory, then my group members would walk you through the rest. So let's get started. All our computers have a memory or a RAM that helps it to run programs, but then sometimes there is not enough space. So the computer would have to use a part of its hard drive as extra memory. The hard drive stores things that the computer isn't using at that moment, but then it swaps them in and out when needed. So if your computer wants to run a program, it gives it out to the computer, but if it doesn't need it at that point, it saves it in that extra memory. And that's all that virtual memory is about. We want to move into the key concept of virtual memory. So for that, we have the paging, page table, page faults, thrashing, and then the translation look aside buffer. Would briefly explain each one of them. So paging divides the virtual memory into pages and then the actual RAM into frames. So instead of loading a whole program, it loads only the needed pages. So all that paging does is to help the computer to run more programs than the physical memory can handle alone. Now I want to move to the next one, which is a page table. So page table is basically a map or an index on the computer that gives the location for each page. So it tells the computer whether the page is in the RAM or on the hard drive. That is all. Now we're moving into page faults. For page faults, we'll be discussing our next slide, so we wouldn't waste so much time on it. So let's jump to thrashing. So thrashing is a situation whereby the system wastes so much time swapping pages in and out without doing any useful work. And this normally happens if our RAM is too little for the work that we're doing. This actually slows down the system. Now let's move to our final one, which is a translation look aside buffer. So for that, it is a small fast cache in the computer's memory that stores recent page translation. So it speeds up the whole memory access process so that we don't have to access the page table every time we need pages. That is basically about the key concepts of virtual memory. Now we want to move into the benefits of virtual memory. The points are self-explanatory, but I'll quickly brief you through it. So what the first bulletin point is trying to say is that it gives program a larger address space, making them feel as if they have more memory than they really do. The second bulletin point is saying that it offers memory isolation so that each program can run safely on its own. The third point is trying to say that it allows more programs to run at once, which improves multitasking. And then finally, it simplifies programming since developers do not have to manage the physical memory directly. That is all about the concept of virtual memory. So moving into our next slide, and my next presenter would continue with it. Thank you.
Hello everyone, I go by the name Kelvin Dela Agbodu, and I'm here to represent or discuss about multi-level paging. So multi-level paging refers to a memory management scheme that reduces the size of page tables in systems with large address spaces, especially in 32 bits and 64 bits. It works by paging the page table itself, that is, using multiple levels of indirections to locate the physical address. So in multi-level paging or in single level paging, each process has one large table, a very big table for systems with large address vectors or addressing space. This table can become very large even if only a small portion of the address space is used. So we talk about multi-level paging so that this paging can divide the table or the page table into smaller pieces to fit into the system. So the basic concept of multi-level paging is breaking down the table into smaller pieces to fit into the system. Instead of one big table, we use a hierarchy, usually one or two or maybe three. to break down the table into smaller pieces to fit into the system. So examples, in case we have a base system, maybe 32, and we want to break it down because it's too big for the system. We have to break it down. We have to split it so it can fit into the system. So breaking down the page table, we have level 1 index, which is the first level the pages goes when you break it down. So breaking a 32-bit system, we break the first bit for level 1 index, we break it into the first system, then we take the other 10, then break it, which goes into the level 2 index. So breaking the 10 for the level 1 index and breaking the 2 for the level 2 index, adding them becomes 20, so which will remain 12. The 12 goes into the offset within the page. So the offset is also a place where when the page is being broken down, it enters as compared to the level 1 then the level 2 index. So we move on to the advantages of multi-level paging. So one, it reduces memory overhead for page table. Also, it's better suited for sparse address spaces. It supports demand paging efficiency. Its capability for large address spaces. Talking about advantages, we also talk about disadvantages. So one, it can increase complexity in hardware and OS. 2, complex memory management. 3, increase context switch overhead. And 4, it increases the number of memory accesses. Thank you.
Hello guys, my name is Kelvin and I'm here to talk about page faults and page replacements. So a page fault is when a program attempts to access a page that is not currently main memory. So this occurs when a program attempts to access a virtual memory page that is not present in physical memory or RAM. So we have types of page faults. We have the minor, the major, and the invalid. With the minor, the page is present in memory but not currently marked as accessible by the MMU. With the major page faults, the page is not in memory and must be loaded from disk. And with the invalid, the page is trying to access a memory location that is not part of its address space, which usually results in a program crash. So we have steps in page faults. So the memory management unit that the MMU detects a page is missing. The CPU pauses the current process. Then the operating system takes over and locates the required page on disk. If the RAM is full, the page currently in memory must be removed, which is also termed as page replacement. The required page is loaded into the RAM. The page table is then updated. Then the process resumes execution. So we have page replacements. So with page replacement, it's when the RAM is full and a new page needs to be brought into memory. Then the operating system chooses a page to remove. So with this, the choice of the page to remove is very critical, as a poor decision can load into frequent page faults and will also reduce system performances. And with this, we have an algorithm which goes along with page replacement. So we have the FIFO, that's first in, first out. And we have the LRU, that's least recently used. And we have optimal page replacement. And we have clock algorithm. So we have advantages of page faults. So with the advantages, it allows programs to use more memory than physically available, that's the RAM, and also prevents from interfering with each other's memory. And we have minor faults allowing sharing of common pages, that's the libraries, across processes without duplications. And applications run uninterrupted while OS silently moves page around or disk. We have also disadvantages. So 1, handling faults involves CPU interrupts, table updates, and scheduling. So disk access time makes page fault non-deterministic. Excessive page faults occur when RAM is oversubscribed, and disk bandwidth consumed by swapping competes with applications or IO operations.
Good day, everybody. My name is Godfrey Sebi, and today I'll be talking about page replacement policy, a concept used in a computer when they run many programs at the same times. When your computer RAM gets full, it needs to make space for a newer data. To do that, it might decide which page to remove. That's where page replacement policy comes in. So when we talk about page replacement policy, page replacement policies are the rules the computer uses to decide which page to remove when the memory is full. There are several common policies of page replacement policy. First, we have the FIFO, that's first in, first out. This removes the oldest page, the one that has entered the memory for a long period of time, but it is not always smart, since the older page might be useful one day. Let's move on to the next policy. That's the LRU. That's the least recently used. This removes the page that has not been used for a long period of time. It is smarter than the FIFO because it tries to keep frequently used page in a memory. The third policy is the optimal policy. This one removes the page that won't be used in the longer period of time. It is perfect in theory, but the computer can't predict the future, so it is mostly used for comparison. Let's move on to the final policy. The final policy is the clock policy, also known as the second chance. This improves on FIFO by giving each page second chance. If a page is recently used, it gets to stay. If not, it can still be replaced. So now let's look at why are these policies important, or the merits or disadvantages of page replacement policy. One, they save memory space by removing unnecessary page. That's one importance of page replacement policy. Second, they keep the system fast by picking the best page to remove. So before they can remove any page, they have to analyze the page before removing any page at all. Third, they keep the system fast by picking the best page to remove. So after the page replacement policy making the analysis, then they will pick the best page to remove. And last one, they reduce error like page fault. So that's the work of page replacement policy. Thank you, everybody. I will leave here for my next presenter.
Hi everyone, my name is Pius Kodom Sapman, and I'm here today to present on segmentation and segmented memory. Segmentation can be defined as a technique of dividing the computer's primary memory into sector or segments. Let's have an example to explain further. The process of dividing potential customers into groups based on their similar interests or characteristics can also be termed as segmentation. The same way the computer operating system puts different or divides data into groups that perform special operations. Unlike paging that uses fixed size pages, segmentation allows better organization, protection, and efficient use of the memory. Let's move on to the types of segmentation. We have the simple segmentation, which is a program divided into logical segments, such as code, data, stack, subroutine, main product, symbol table, etc. We've seen simple segmentation in our lives day in, day out, such as a file which has its segmented data in it in a zip. It's an example of simple segmentation. Let's move on to the second type of segmentation, which is the virtual memory segmentation. And this divides the memory of process into the number of continuous segments rather than fixed page sizes compared to paging. So we have here an illustration of how segmentation works. Let's not forget that it has been segmented. So to find the real physical address, this is how we find it. This illustration, I'm going to debrief you how we actually find the physical memory of a segmented memory. So you can see that we have three parts here, which is the CPU, limit base, and the physical memory itself. So we are going to talk about how everything will be done to get your physical address in the physical memory. So we have the CPU making out S and D, S being the segment number, D being the offset. If you wonder what the offset is how far you want to go in the segment memory. How far you want to go in the segment memory. I'll debrief everything. So you can see the S going to the limit base to check whether it's portable or it pairs with the offset. So we go to the limit base and we come back to the less than sign, and we can see that the offset to leads down to the less than sign. And this is what happens here. To find the physical memory, we first have to check if the segmented number pairs with the offset number. So this is how we check whether it pairs with the offset number. You find whether the offset number is less than the base number, which is the one in the segmented table. So that's what the illustration shows right now. You check if the offset is lesser than the base to find the real address of the segmented part. So after finding if the offset is lesser than the base, then we go ahead to add the base to the D, which is the offset. So to really find the physical address, you add the base to the D after finding out that the offset is lesser than the base. And that's what the illustration shows. So if not so, if the offset is greater or equal to the base, then we are addressing an error. That's what shows in the illustration. Else it's going to crash or it will cause a corruption if the offset is greater or equal to the base. And that's what we have in the illustration there. We move to the concept of segmentation, and we have here segment table, which I've already said that segment table is maintained by the OS that maps segment numbers to their base address. So to find the main address of a segmented part, you need the base address in which the segment table has it. And we have the logical address, an address used by the program consisting of segment number and an offset. I also talk of an offset, which is the number in addition to the base number to find your physical address. And we have the physical address, the actual address in the physical memory where data is stored. So to get whatever is in the segmented parts, you need to get to the physical address, and that's what we talked about in the illustration. Thank you, and my next presenter.
Thank you, teammates. Once again, my name is Cheryl Dulcie Champon, and I'll finish up with our presentation by talking about virtual and segmented memory. So from our previous presentation, we came to see that virtual memory is a way for the computer to act like it has more memory than it does. We also came to see that it splits the memory into pages and frames, and it moves data between the RAM or the physical memory and then the hard drive. And as a result of that, it helps our computers to run more programs than it actually can, all by itself and at once. Now I want to move to segmented memory. What is it? Segmented memory is a way that the computer organizes memory into parts based on what the program is doing, meaning the memory is split into segments and parts based on what it's going to be used for. So for example, for codes, it is for the instructions that the computers run. For data segments, it is for string information like numbers and words. And then for stack segments, it is for keeping track of functions, for function calls, and to also help the programs to remember what to do next. Now for segmented memory, programs access memory by giving a segmented number and offset. So it's like saying that start here, then move forward a bit, as seen from the example in the slides. Now I want to look at some key features of segmented memory. They are self-explanatory, but I'll take you through them. So the first point is trying to say that the segments can be divided into different sizes. Also, they are good for keeping codes, data, and stacks separately. They also help with organizing programs, allowing the programs to grow and to also keep it protected. And then finally, it can be used along with paging. Now there's a table below that gives a difference between virtual and then segmented memory. It talks about its memory division, the block size, the management, the wording used, but because we've already discussed it, when you read it, it is self-explanatory, you would understand. That's it for virtual and segmented memory. To wrap up our presentation, we've looked at virtual memory, paging, page faults, page replacement policies, multi-level paging, and segmentation. These techniques, when they come together, helps our computers to manage their memory effectively and to also run programs smoothly, even with limited RAM. This is the end of our presentation. We're open to questions. Thank you.